Hi students. Here you're going to learn about another interesting topic, and that is the generator polynomial of cyclic code. Okay, we all know what is a generator matrix of a linear block code, right? That is, in a generator polynomial, we for a generator matrix for an nk linear block code, we represent the equation using v is equal to u into g, right? Where v is a 1 by n row matrix, u is a 1 by k row matrix, and g is a k by n matrix, right? So this is how we define the generator matrix. That is in the case of an nk linear block code. Okay, now just like this, for a cyclic code, okay, for a cyclic code, the equation we represent for the code word for the cyclic code, that is by using polynomials, right? So the equation is represented by v of x is equal to u of x into g of x. This is how we represent the equation. Capital letter, everything should be in capital letter. Okay, this g can be represented in small letter. G can be represented small letter. Every other polynomial should be in capital letters. So capital letter v of x is equal to capital letter u of x into g of x. Okay, so what is v of x and what is u of x? We can understand from all these terms when you compare these two equations, right? See, we all know that v is the transmitted code word or the output code word, which is of n bits. That is represented as v0 plus v1 plus v2 up to vn minus 1. So it's code polynomial. So this is of n bit, right? N bit. So we have this code polynomial. The code polynomial is represented as v of x, which is nothing but v0 plus v1x plus v2x square plus up to vn minus 1 x raised to n minus 1, which shows a degree of n minus 1. Okay, degree of n minus 1. Now, same way, what is u? U is a k bit. It is the code word. We all know that that u stands for the input message. It represents the input message, and we all know that for an nk cyclic code, just like in the same case of an nk linear block code, right? In the same way, for an nk cyclic code, this n represents the number of output bits, that is this one over here, and k represents the number of the input bits, that is the u over here. That is, u is represented as the input or the input message. So and its bit, and the number of bits is k. So it starts with u0 plus u1 plus u2 plus, and it goes on up to uk minus 1. This is how the message bits are represented in u. Okay, it starts from u0 to uk minus 1. So totally there are k bits, just like over here, right? Over here it is u0 to uk minus 1. So therefore, u of x, that is the polynomial for u, the input polynomial, it's called as the input polynomial of u, is represented as, just like this, it's represented as u0 plus u1x plus u2x square plus, and it goes on up to uk minus 1 x raised to k minus 1. So now if you compare these two equations, you can say that u of x is having a degree of k minus 1. So v of x is having a degree of n minus 1 and u of x is having a degree of k minus 1. So in that case, how do you define g of x? You see, you multiply a polynomial with k minus 1. You multiply a polynomial with degree k minus 1 and you multiply g of x. You should get a polynomial of degree n minus 1. And that is only possible if g of x has a degree of n minus k. So g of x has a degree of n minus k, because if you want v of x to have a degree of n minus 1, and we know that the degree of u of x is k minus 1, then you have to multiply a polynomial of degree n minus k with u of x, so that you will get a polynomial of v of x of degree n minus 1. That's the only way this equation can be satisfied. That is, one polynomial should have a degree of n minus 1. This polynomial has a degree of k minus 1. So what should we multiply with this polynomial so that you will get a polynomial of degree k n minus 1? You need to multiply this polynomial with this polynomial. That is a polynomial of degree n minus k. So therefore, we conclude that g of x has a degree of n minus k. But that is not the only interesting thing about this g of x. You see, if you see this, let me explain this whole thing with you using an example. Okay, suppose, okay, your message u, okay, I'm going to represent u as 1011. Okay, I'm going to represent u as 1011. So it's a 4-bit. Okay, this is a 4-bit message. Okay, let me say let's say that I'm using a 74 cyclic code. Okay, I'm using a 74 cyclic code. Just example, let's using this as example. 74 cyclic code. So 74 cyclic code means the number of input bits is 4. That's why there are 4 bits over here, and the number of output bit is 7. So the number of bits of v should be 7 bits. Okay, and so since the number of bits of u is 4, the degree of the u of x, the degree of u of x must be 3. So how do I express this equation? How do I express the polynomial of this? U of x is equal to 1 plus 0 into x, which is 0, plus 1 into x square plus 1 into x cube. So therefore, u of x is equal to 1 plus x square plus x cube. This is the polynomial of this code word. This is the polynomial. Here you can see that the coefficient over here is x raised to 0. That is the 0th position over here. And the coefficient of x raised to 1 is 0 because the second bit is 0. That is why you don't see x raised to 1 over here, because 0 into x raised to 1 is 0. That is why you don't see x over here. And here 1 into x square is x square and 1 into x cube is x cube. So this is how we represent the polynomial. Okay, so assume that u of x is equal to this one. Okay, now and let me say that g of x. Okay, my g of x, I'm going to choose, okay, example, I'm going to choose g of x as 1 plus x cube. So what is my v of x? V of x is equal to u of x into g of x. Okay, so which means we all know what is u of x, which is 1 plus x square plus x cube into, and g of x is 1 plus x cube. So if I go to multiply, if I go to cross multiply, I will get 1 plus x cube plus x square plus x raised to 3 plus x raised to 5 plus x cube plus x raised to 4 plus x raised to 6. This is the polynomial v of x I'm getting. Okay, v of x I'm getting. Okay, see, one interesting thing about this, like I said, this plus actually represents the modular 2 sum. Okay, you see over here x cube plus x cube. Okay, if you see two same terms, you can cancel each other, because x cube plus x cube, what is x cube plus x cube? What is x cube plus x cube? X cube plus x cube can be written as x cube. You can take x cube common and you will get 1 plus 1, and we all know what is 1 plus 1. 1 plus 1 is 0. So x cube into 0, which is 0. That's why I'm saying you can cancel any two terms that are having the same power. Okay, so over here you can say that x cube and x cube have the same power, so I can cancel each other. So they will cancel. Let me cancel both of them. Is there any other same terms like that? No, there's no other same terms like that. So I'll get v of x is equal to, is equal to 1 plus x plus x square, 1 plus x square. Then of course there's x cube over here, x raised to 4 is over here. Let me write that, x cube plus x raised to 4 plus, then we have x raised to 5 and x raised to 6 plus x raised to 5 plus x raised to 6. So this is the code word. So therefore I can say v is equal to, what is the position of the first bit? 1. Second bit is also exists, so it's 1. Third bit is also 1. Fourth bit is also 1. Fifth bit is also 1. Sixth bit is also 1. Seventh bit is also 1. 1, 2, 3, 4, 5, 6, 7. See, so this code word has 7 bits. This code word has a 7 bits, but its polynomial is of degree 6. That is, if the code word is of n bits, the polynomial has a degree of n minus 1. So you see the degree of this polynomial over here is the highest power, which is 6. So therefore the degree of this polynomial is 6, but the number of bits is 7. So this is one interesting thing. But okay, but that's not the only story that you see. Let me change how would I do this? Is I simply assumed the value of u, I simply assumed the value of g, and then I simply substituted and multiplied all of them, and I got this answer. Now let me use another letter. Okay, let me use another bits for u. Let u, okay, this time I'm going to make u as which one should I give? I'll give this number 1100. Let u be equal to 1100. Okay, and g, okay, if u is equal to 1100, then what is the value of u of x? U of x is only equal to 1 plus x. See, this is one interesting thing you can see. Why it is 1 plus x? Because the last 2 bits are 0. So it is so here you will actually get 1 plus 1 into x plus 0 into x square plus 0 into x cube. But 0 into x square is 0 and 0 into x cube is also 0. So 0 plus 0 is again 0. That is why you get u of x is equal to 1 plus x. But so here, even though the number of bit is 4, the degree is actually lesser than 4 minus 1. Even though the degree here, even though the number of bits is 4, the polynomial over here is less than k minus 1. So that also can happen. It can happen when the last bit is 0. Okay, so therefore the degree of a polynomial may not always be n minus 1. The highest degree can always be n minus 1, but it cannot go greater than n minus 1. It can either be the degree of the actual degree of the polynomial can either be n minus 1 or less than n minus 1. So here you can see I'll prove that over here to you. So this, like I said, I'm using 7/4 cyclic code. Okay, again I'm assuming that I'm using 7/4 cyclic code. So 7/4 cyclic code means you all know that the number of bits of input bit is 4. That's why here you can see 4 bits, but the number of output bits should be 7. Like this, it should be 7. Let me see what do we get over here. So if for this example, my g of x is going to be the same. I'm going to choose the same g of x, 1 plus x cube. Okay, 1 plus x cube. Okay, I'm going to choose the same g of x. Okay, and then what I'm going to do is that I'm going to multiply v of x again with u of x and g of x and see what answer will I get. What will happen? That is, this is nothing but 1 plus x into, and what is g of x? 1 plus x cube, and on multiplying both of them I will get 1 plus x cube plus x square plus x raised to 4, right? Plus x square plus x raised to 4, and yeah, that's it. This is the answer. Or in other words, you see x plus x is 0, right? So I can cancel these two terms. X plus x is 0. So what do I get? I get the answer as 1 plus, what's the next number? X square plus what's the next number? X cube plus what's the next number? X raised to 4. You see, look at the degree. Now look at the degree of this polynomial. It is supposed to be 6. The degree of the polynomial is supposed to be n minus 1, but instead it is less than n minus 1. It is, the degree is 4. Here, because the value of n is 7, right? If the value of n is 7, then the number of bits must be equal to 7, but the degree of the polynomial should be n minus 1. But here, the degree is not n minus 1, it is less than n minus 1. How did this happen? Because of this. Because the u of x has a lesser degree. That is why v of x also has a lesser degree. What is that? But how do you express? Do not make that mistake. How do you express the code bit of this? How do you express the code word of this? The code word is always 7 bits. Okay, it's always 7 bits. So if you see this over here, the code bit can only be represented as 1, 0, 1. This is 0, 1, 2, 3, 4. Okay, 5, 6, 7. This is the code word of v of x. Okay, Here you can see the number of bits is 7. It has to be 7. That is why we are calling it as a 7-4 cyclic code, because the number of input bit must be 4 and the number of output bits must be 7. So definitely the number of output bits should be 7. Okay, but even though the number of output bit is 7, the degree of the polynomial can be less than 6. So therefore we can say that the degree of the polynomial is always less than or equal to n minus 1. Okay, the degree of a polynomial, of a degree of a code with a polynomial of a code word of n bit has a degree of less than or equal to n minus 1. It may not be always be equal to n minus 1. It can also be less than n minus 1. Okay, I can write that as a statement. That is, a code word of n bit has or can be represented by a polynomial whose degree is less than or equal to n minus 1. If it is a code word of k bit, then can be represented by a polynomial whose degree is less than or equal to k minus 1. Because the reason why it happens is because sometimes the last 2 bits can be 0. Sometimes the last bit can be 0, or last 3 bits can be 0, or the last 4 bits. So because of that, the degree will become reduced. The degree of the polynomial becomes lesser. And if we multiply that degree with the generator polynomial, with the g of x, we'll get the output polynomial, and that degree also will be less than n minus 1. You see, so that is why. So it may not be always be n minus 1. It can be less than n minus 1, but it can never be greater than n minus 1. So this is one thing you have understood. But in both the examples, if you have looked very carefully, you can understand one small trick that I have used here. In both this example, even though v of x has a degree of less than or equal to n minus 1, even though the degree of u of x has a less than or equal to k minus 1, even though both of them have that kind of a degree, the degree of g of x, in both the case, the degree of g of x is always constant. That is one of the important property of g of x. That is, g of x has a constant degree of n minus k, exactly equal to n minus k. That is the degree of u of x can be k minus 1 or less than k minus 1. The degree of v of x can be n minus 1 or less than n minus 1. But the degree of g of x is exactly equal to n minus k. And that is one important property. That is, g of x, the degree of g of x. The degree of g of x must be exactly equal to n minus k. Must be exactly equal to n minus k. It should not be less than n minus k. It should not be greater than n minus k. Because if it becomes less than n minus k or greater than n minus k, then this equation will never be satisfied. You will never get the right degree. You will never get the right degree for v of x on u of x, for the corresponding u of x. You will never get the right degree for v of x for the corresponding u of x if this statement is not satisfied. So the degree of g of x must be exactly equal to n minus k. So let me ask you this one simple thing. So if you see this g of x, so let me represent g of x, since you all know how to write g of x. So g of x can be written as g0 plus g1 into x plus g2 into x square, and it goes on up to the last term should be a degree exactly equal to n minus k. So this is it there. The last term will be looking like this. That is g0 up to gn minus k. Okay, g0 to gn minus k. So there will be n minus k plus 1 terms, I believe, right? There will be totally of n minus k plus 1 terms. Okay, and over here you can see that the x is last letter is x of n minus k. You remember, if you look very carefully in the terms of u of x, okay, in u of x, the last term is of degree k minus 1 because the degree is k minus 1. Here, if you look at v of x, the last term is vn minus 1 x raised to n minus 1. So here the degrees, the last term has x raised to n minus 1. That is why the degree is n minus 1. But in the case of g of x, the degree must be n minus k. So therefore the last term is n minus k. Okay. But like I said, the most important word in this entire sentence is this: exactly equal to. It should not be less or it should not be greater. So that is what is here. But if you look at this polynomial, all these values, just like how I represented u of x over here, you see, even though u is 4 bits, there are only 2 terms. Here you can see that here, even though v is having 7 bits, here there are only 4 terms, 5 terms, 1, 2, 3, 4, 5 terms, and the remaining 3 bits are 0, right? So in the same way, over here also, that should not happen over here. Like I said, it should be exactly equal to n minus k, and that is only possible, that can only be possible. This degree, if you want this degree to be exactly equal to n minus k, then this term and this term must be equal to 1. Both of them must be equal to 1. The value of the remaining coefficients in between can be any number, it can be 1 or 0. But if you want this polynomial to be of degree n minus k, only if its degree is exactly equal to n minus k only, I can apply this equation right here. So if you want this degree to be exactly equal to n minus k, the only way to assure that is by putting the value of the coefficient of the first term and the coefficient of the last term should be equal to 1. That is the only way. Because you see, if this value have been equal to 0, just imagine, just think to yourself, if this coefficient was 0, you will get 1 plus x square. You're supposed to be, here you can see it is 7 minus 4. Here for a 7-4 cyclic code, for a 7-4 cyclic code, what is 7 minus 4 is 3. So the polynomial degree of polynomial is 3. But if the last term was 0, then it will become 0 into x cube. So therefore that degree of polynomial 3 will become reduced, it becomes 2. You see, so that value will vanish if this had been 0. That is why the first coefficient and the last coefficient, same way in the last coefficient also, if this coefficient was 0, then you can take x common out, and if you take x common out, again the degree will be reduced. See, so that also should not happen. So that is why, in order to assure that this generated polynomial is of a degree exactly equal to n minus k, the first coefficient and the last coefficient, that is g0 is equal to gn minus k, should be equal to 1. That is one of the important property of g of x. That is the coefficient of the first term and the coefficient of the last term must be 1 and nothing else. That is a very important property. And since we already know, in the last class we learned about the multiplication modula of x raised to n plus 1, right? We learned that. We know that v of x is a factor of x raised to n plus 1. Okay, so we know that. Just keep that in your mind. So here you can say that when I'm going to say that v of x, okay, v of x is equal to u of x into g of x. Okay, let me write this whole thing again. So in that case, v of x can also be written as v of s. Now look at the beauty part over here. V of x can be, let me expand u of x. U of x can be written as u0 plus u1x plus u2x square plus up to uk minus 1 x raised to k minus 1 into g of x. Okay, or this can also be written as u0 into g of x plus u1 into g of x into x plus u2 into g of x into x square plus, and it goes on up to the last term is uk minus 1 into g of x into x raised to k minus 1. Okay, So you see, you know that this u0, u1, u2, u3, all these values that you see here are nothing but ones or zeros. Okay. Now we all know that this code word, this depends on the value of the message bit. Suppose, okay, suppose let the message be 1000 up to all zeros. That is only the first. Just assume that we are using this message bit. That is only the first number. That is this number right here is 1, and the remaining numbers are 0. Just assume that. What you will get in that case? What you will get? V of x will now become u0 is 1, so it becomes g of x plus u1 is 0, u2 is 0, u3 is 0 up to uk minus 1. All are zeros. So you will get all 0, which means you will get nothing but v of x is equal to g of x. So what do you understand from here? From here you have understood that g of x is also one of the core polynomial of v of x. That is the another interesting property of g of x. That is g of x is also one of the core polynomials. So we can say that, just like how I said that v of x is a factor of x, that is x raised to n plus 1, I can say that g of x is also a factor of x raised to n plus 1. G of x is also a factor of x raised to n plus 1. Okay, and another interesting thing that you have also learned is that if you cyclic shift v of x, you are getting another valid code word. It's that same theory can also be applied over here, which means if you apply the cyclic shift to this polynomial also, that polynomial is also one of the valid polynomial. In other words, you see how everything is now being unified. So in other words, if you want to write the v of x code, you can simply write the value of g of x, because the first code word of g of x, the bits of g of x, g of x is also one of the code word. It's also one of the code word. Okay, and that code word, and if you cyclic shift that code word, that is also another valid code word. Again, if you cyclic shift that code word, that is also another valid code word. So you see so therefore in conclusion I can say that g of x is also, just like how I said v of x is a factor of x raised to n plus 1, but when you cyclic shift it, then becomes a remainder becomes the remainder is the cyclic is the shifted version, is a shifted word. Same way over here also, g of x is also a factor of x raised to n plus 1. So in other words, what have we all studied so far? What you have studied in this entire video, the summary. Let me just give you a summary of what you have studied so far. That is, first thing is that u of x, okay, u of x can be represented as u0 plus u1 plus u2 plus up to u k minus 1 x raised to k minus 1, which means the degree of u of x, is less than or equal to k minus 1. That is the first thing you have studied. Second thing you have studied is v of x, which is you have already studied the first video. That is v of x is v0 plus v1 plus here I forgot to put x, and here it is x square. Okay, here also v1x plus v2x square plus up to vn minus 1 x raised to n minus 1. So therefore this is also a degree of v of x is also less than or equal to n minus 1. It may not be exact, it may not be always be n minus 1, can be less than minus 1, especially just like in this example I have used here. If the last bit or the last 2 bits or the last 3 bits or the last 4 bits are 0, then the degree according to that the degree will also get reduced. That is why I say it is less than or equal to n minus 1, and here the degree is less than or equal to k minus 1. But it can never go greater than k minus 1, and this can never go greater than n minus 1. Okay, but for g of x, now that is an interesting property. The g of x, as I've written over here, the degree must be exactly equal to n minus k, which means the first term and the last term, the first coefficient and the last coefficient must be equal to 1. Or in other words, g of x, whatever happens, g of x should always be, let me write this again, g0 plus g1x plus g2x square plus up to gn minus k x raised to n minus k. So if the first term and the last term is 1, then this will become 1 plus g1x plus g2x square plus, and it goes on up to, and the last term is also should be 1. So you will get, let me write like this, let me write the term before this, that is j of gn minus k minus 1 x raised to n minus k minus 1. It's the term before this, plus, and the last term here, this term should be 1. So this will become x raised to n minus k. Okay, this is the one beautiful thing you'll understand from here, that is the first term is 1, the coefficient of the first term is 1, and the coefficient of the last term should also be 1. Okay, this is 1. This can also be written as 1 plus, if I want to combine all these terms, I can put sigma I is equal to 1 to n minus k minus 1, because the last term over here is, the second last term over here is n minus k minus 1. So I is equal to 1 to n minus k minus 1 g I x raised to I plus, and the last term of course will always be x raised to n minus k. This is what how g of x will look like. That is, this g1, g2, g3, g4, g5, g6 up to gn minus k minus 1 can either be 0 or 1, but the coefficient of the first term and the last term must always be 1. Okay, so which means, that means what it means is that, suppose, okay, if you are seeing a 7-4 cyclic code, if you are seeing a 7-4 cyclic code, and if you simply look at the polynomial, okay, if you look at the polynomial, the first letter should always starts with 1 plus something, it will be something over here, plus the last term should always have this, because 7 minus 4 is 3, n minus k. So the last term in between can be anything. Okay, it can be x plus x square, or it can be x square, or it can be x, it can be any number, but the first number should always be 1, just like this, and the last should always have the x raised to the difference between the output bits and the input bits. Always, this is how the generated polynomial of a nk cyclic code should look like. Okay.